When scheduling tasks with hierarchical dependencies, a common constraint is that choosing a parent task prevents you from choosing any of its immediate children. Evaluating every combination using standard recursion rapidly multiplies decision paths, causing an unviable O of 2 to the n time complexity. Dynamic programming on trees changes this. Instead of calculating the entire tree, we isolate local decisions between a single parent and its children. By computing the best possible value for a subtree once and returning that result to the parent, we remove the need to revisit those lower nodes as we move toward the root. To find that local optimal choice, every node must determine two values: the maximum profit if that node is taken, and the maximum profit if it is skipped. In many DP problems, these results are stored in an external grid or table. In tree DP, there is no separate array holding these answers. These values live on the recursive call stack. They are passed directly upward from child to parent as each function call returns. Success in tree DP depends on the transition logic, the specific rules a parent uses to calculate its own two states based on the data handed up from its children. Because a parent state depends on its children's values, the children must be mathematically solved before the parent can begin. This sequence is a post-order traversal, a depth-first search pattern ensuring we visit every child before processing the node itself. Moving through the tree guarantees that when reaching a parent, its descendant subproblems are already solved and ready to use. We can see this in action using the simplest possible unit: one parent node and two leaf children, each with an empty slot for their skip and take values. How numbers flow through this three-node structure defines the logic for every other connection in the tree. At the bottom of the tree, child A has a take value of 50 and child B has 30. Their skip values are 0 because there are no nodes below them to contribute. When we choose to take the parent node, the children are restricted and must be skipped. The parent can only add the children's skip values, which are both 0, to its own total. Moving to the parent's skip state removes the restriction from the children. Skipping the parent doesn't mandate a specific action for the nodes below. This creates an asymmetric constraint. If skipped, the children have the freedom to choose whichever of their two states yields a higher profit. If skipped, which values from the children move up to the parent? The parent takes the maximum value from each child. Here, 50 and 30 move up, giving the parent a skip value of 80. This logic, locking children when a parent is taken, but allowing a choice when skipped, is the core mechanism for resolving independent set dependencies at every level. Translating this model into code shows that the state machine fits within a standard depth-first search function. The two return values we visualized can be captured directly using structured bindings, making the take and skip states easy to reference. The code processes the children with recursive calls before it runs the parent's logic, which naturally implements the post-order traversal we discussed. Since each node is visited exactly once, the algorithm runs in O of n time, avoiding the growth limits of the brute force approach. When a problem involves hierarchical exclusions, using a post-order traversal to bubble up state pairs provides a direct path to a linear time solution.